PCB Foundations, by Paul Taubman and Sean Kelly. Presented by 9.Connects. Chapter 5. Specification Writing. 5.1. Introduction. Before starting a new project, a clear understanding of the requirements of the PCB should be agreed upon. There are too many factors for these requirements not to be written down, especially when more than one person or group will be involved. There are many benefits to a written document. Though the specification is not a legal contract, those who contribute to it may treat it like one, and by contributing their knowledge to it, they will also support it. The better it is written, the less likely there is room for varying interpretations, which can lead to conflict of ideas or interests. 5.2. Stakeholders. In an optimal design environment, not only would there be time allocated for specification writing, but it would also bring together all parties who had a stake in the design. All too often, the group that starts the design calls all the shots. Those who are further along in the design process are left to handle issues which were not given adequate thought at the start. For example, those who will be responsible for testing and possible debugging of the device can save dozens of workdays, if not weeks, if their input regarding testability was considered earlier in the design process and written into the specification. Who are stakeholders in a PCB design project? Here's a partial list. Electrical designers. Anyone who has a part in the electrical design of the unit. In addition to those who will contribute to the circuit on the PCB, this may include system designers, if the board is part of a larger electrical system. Software or firmware designers should also take part if their task will be to program any devices on the PCB, especially if the board contains FPGAs, microprocessors, DSPs, or microcontrollers. They will need to know what function or functions they will be programming into these devices, and more importantly, an agreement as to how they will access such components for programming. Mechanical designers. This should be obvious, and yet, it is widely overlooked. Unless the board has no other purpose than to sit on a lab bench, there will be a need for a mechanical enclosure, or to ensure a good fitment in a larger system. With today's collaboration capabilities between EDA tools and the mechanical tools, there is no excuse for not working in close cooperation with the mechanical team. Fabricator. Most designers tend to leave the fabricator out of the discussion until the PCB layout is ready for fabrication. This was acceptable 2 or 3 decades ago when the signal speeds were slow, and the universal material being used by every design project was FR4. The speeds of the circuit now require a careful planning of the layer stack-up to minimize crosstalk, provide the copper necessary for current return paths, to mitigate overall noise, and to select materials that will best suit the impedance needs of the board. By providing the frequencies of the key signals and their impedances, the fabricator can propose a layer stack-up, develop design rules, and give a cost estimate. Test engineers. These folks bear the brunt of the issues that are caused by lack of specification and planning. All too often, test engineers must perform miracles to allow them to debug a board, because the designer never took DFT into consideration. The cost could be in weeks of schedule slippage. As mentioned in the prior chapter, if you are the designer, design the board as if you are responsible for testing it. Purchasers. What we do not see on the engineering end is the effort by the purchasing folks to ensure that the components meet environmental requirements, either set forth by the company or by the government, export requirements, lead times, and component obsolescence statuses. Inviting them to contribute to the process early on allows everyone to understand the ground rules when it comes to purchasing. In addition, it allows the design team to explain why they may need something that is outside the normal procurement process. Marketing. Business and engineering mix like oil and water. Designers can engineer some amazing things, but, in the end, the product must be marketed and sold to the target audience. A good marketer can not only provide input to the design team as to what they think the market or customer has an interest in, they can also pitch the design team's intent to other groups. Management. Although these meetings should be run by management, a good designer will and should run such meetings if the manager is not proactive in the project. Management is always concerned with schedule and cost, however, meetings of this nature allow the manager to see the value added from having a specification. If a manager is declaring that writing a specification is a fruitless endeavor, and demands that you start pounding away at a design, it's time to look in job postings. In the end, you know exactly what is going to happen if this specification is not created, and there is no reason for you to take the brunt of it when the project inevitably crashes and burns. Do these shareholders have to always be there for every specification meeting? The answer is no. There will be multiple meetings as the document progresses. The key objective is to get buy-in from all appropriate parties. The specification not only provides marching orders, but it is also backed by all shareholders who were given an opportunity to provide their input. For the designer working in a company, or environment where multiple hats are worn, a specification is still a valuable document. When we write something down, we subconsciously commit to it. 5.3. Where to start? The rest of this chapter will delve into the nitty-gritty details of specification writing. Do you have to follow this to the letter? Absolutely not, unless your company requires it. The key point is to get what needs to be done in writing. At the end of the day, it's better to have a so-so document than nothing at all. Prior to any specification, you may want to produce the classic napkin drawing. Countless, ingenious, and spontaneous ideas have started over dinner conversations or cocktails, in which the idea was drawn on a napkin. Even if you are sitting at your desk with a cup of coffee and a piece of paper rather than a napkin, an exercise of this nature allows you to noodle on different thoughts and ideas. It can be words, blocks to represent functions, a drawing of the product, etc. If you are working with others on the project, seed the specification. By seeding, you are basically writing what you believe and know to be the design, and putting forth what you believe to be the requirements. It does not have to be complete. It should start as a list, or outline of ideas and topics. Engineers take pride in their work, and often get their feathers ruffled or take it personally when their work is scrutinized. Do not be offended when your document is scrutinized. Once this coarse grit sandpaper of a draft is handed to everyone, they will nitpick it. This is to be expected. In fact, if they do not provide feedback, they more than likely did not read it. Keep in mind that when everyone contributes to the document, they are signing on to it. They are not crushing the seed, they are nurturing it. Take ownership of the document. As feedback comes in, and as various aspects of the requirements become clear, the requirements will emerge. A specification, if written correctly, will list viable requirements. Good requirements are testable by their nature. 5.4. Good requirements. Although this list may look intimidating, one does not have to be a professional writer or an expert wordsmith. In fact, the best requirements use the simplest wording. One may have to use jargon of their trade, but nothing stops the writer from creating a glossary of terms within the specification. It is also important to note that if one uses a particular name to describe a component, or an aspect of the project, one needs to be consistent in using the name. This is an issue that happens in large companies, where acronyms are created practically on a daily basis. 5.5. The use of shall. In military-style requirements, the word shall has a significant meaning. Though you may not necessarily work for the military, the use of shall forces the individual writing the requirement to think carefully about the wording of the requirement. The word shall denotes the requirement as being necessary. Words such as will or may denote optional requirements. These are requirements that could possibly be implemented in the design, but are not mandatory. 5.6. And or. As the document progresses, it will look like a list of sentences. Each requirement is its own sentence, and in some cases a paragraph, if clarification is necessary. The use of the conjunction words and, or, is a possible indication that there are two requirements in one. For example, the widget shall operate in temperatures between -55 degrees Celsius and 85 degrees Celsius. In this example, the sentence consists of two requirements. From a test point of view, it would require two completely different test environments, one that would be sizzling hot, and the other brutally cold. Therefore, this requirement is better suited to be written as two requirements. As mentioned earlier, simple sentences are fine. The widget shall operate in an environment up to 85 degrees Celsius. The widget shall operate in an environment down to -55 degrees Celsius. 5.7. Subjective wording is to be avoided. The use of subjective words leaves the requirement open to interpretation. This is not only an opportunity for a designer to take liberties with the requirement, but in an extreme situation, may also allow a customer to withhold payment until it is done the way they arbitrarily interpret the requirement. Fortunately, documents of this nature are generally not provided to the customer, unless it is part of the contract to do so. Even if they are not shared with customers, subjective wording may lead to arguments within the design team. In many cases, the designer is not privy to the budget and may, as the old saying goes, deliver a Cadillac when the customer paid for a Chevy. 5.8. Additional information. Information that helps support any of the requirements is encouraged to be added, such as circuit drawings, tables, charts, and references to supporting documentation. It is important that the reader is aware that this information is not an actual requirement. For example, if one has a preliminary idea for a circuit, it will help to have it added to the document. The statement within the document could read as follows. The circuit shall contain a reset delay. An illustration of a possible reset delay is presented. 5.9. The construct of a requirement. When we get into the lowest level of the requirement, the structure becomes apparent as entities, action, conditions, constraints. Here are the definitions of these elements that make up a requirement. Entities. The subject of the requirement, and the object of the action. Actions. What the subject does, and contains an action verb. Conditions. What must be in place for this action to happen. Constraints. Qualifies the action or performance. Here are a couple of examples. Example number 1. The height limit of the components on the PCB shall be 1 inch on the top, or component, side. Entities, components. Action, the verb phrase shall be, as in, its existence or presence. Condition, components on the PCB, specifically the top, or component, side. Constraint, limit of 1 inch height on the component side. Example number 2. The PCB stack-up shall consist of 8 copper layers. Entities, PCB stack-up. Action, consists. Condition, the existence of the PCB stack-up. Constraint, 8 copper layers, no more, no less. 5.10. Testability of the requirement. When writing a requirement, a method of verification needs to be considered for testing the end product. This practice is important, since it is verifying that the requirement is well written. It also requires the design team to look at the feasibility. For example, if the requirement requires the ability to travel back in time, the design team better have a feasible way in mind for this to work, that is testable. The table presented here provides the verification methods of a requirement, including analysis, demonstration, examination, test, and certification, as well as their accompanying definitions. Some requirements may need more than one verification method. Also, note that there could be a very fine line between verification methods. For example, demonstration and test have similar methods. The best way to determine between demonstration and test depends on the audience to which it may be presented. For example, if a consumer product is being demonstrated that happens to be powered by two 1.5-volt batteries, the audience expects this to work. A multimeter does not have to be connected to the device to show that it operates at 3 volts. This would have been done under the verification method of test. Pick and choose these test methods carefully. Some of them will require a good deal of time and effort. For example, consider a project team that wants to use a connector for space flight that has not been certified by the manufacturer for such use. This connector will require analysis for initial feasibility, and testing thereafter. This may require thousands of dollars in software and test equipment. Whereas, if they use a connector that has been certified by the manufacturer, the requirement is verified by simply providing the manufacturer's certificate, or by demonstrating that the connector has been used successfully in similar projects. 5.11. Specific to PCB requirements. We have provided a fair amount of detail as to the mechanics of specifications writing. What are the PCB attributes to be included in a specification? Here is a brief list. Mechanical attributes. The schematics represent the conceptual aspect of the design, which does not consider the physical dimensions. Having physical dimensions provides these bounds. The mechanical dimensions may need to be changed as the design progresses, but it is far better to consider this up front, than to find out later that the circuit will not fit within the physical space provided. The shape and size of the PCB should be based on function and fit requirements. With today's fabrication processes, odd shapes can be made quite easily, although it is far easier for the fabricator and assembler to work with rectangular boards. Height requirements are necessary to ensure that the board can fit in the enclosure or system that it was designed for. The mounting of the PCB within a chassis or system should be determined. All too often, mounting holes are moved without regard as to the impact of the PCB layout. Component placement. Key component placements need to be considered. High pin count devices, like FPGAs, microprocessors, and DSPs, need to be placed towards the center of the board, so that the route can escape on all 4 sides. The placement of connectors, and other devices used to communicate on and off board, need their due consideration. With the advent of high-speed communications, placing a connector has consequences for the area of the board surrounding it. Most electromagnetic noise transmitted through the PCB will be through the connectors. Antennas, if required, need their space and shielding. Calculations and best practices for termination and filtering need to be captured in the specification. Thermal and noise management from power regulators require careful attention. Follow the device's vendor recommendations, and review application notes. FPGAs and large multi-pin components require a number of capacitors to assist in both AC noise reduction and power reservoirs, to prevent voltage rail collapse. Refer to the datasheets for more information. We recommend caution when reading application notes, especially when the notes are providing recommendations for circuit configurations. Unfortunately, a number of these application notes are written without being tested in the labs and confirmed. If the explanation is not adequate or clear, contact the component manufacturer. Testability. When it comes to specifications, one must consider the how-to of testing. In fact, some specifications are written in 3 columns. 1. The requirement. 2. The test method, analysis, demonstration, examination, test or certification. 3. A note column that may describe what equipment will be used, the organizations that may perform the test, the need to create test equipment, accommodations to the PCB, etc. Therefore, if special connectors or clearances are needed for test, the specification should capture this information. The example provided here shows a requirement along with the test method and note regarding the requirement. 5.12. Chapter Summary. In conclusion, specification writing is 1. Important. The best managed projects have specifications to back them. 2. Efficient. The time it takes to write a specification easily makes up for the time that would be spent in email, meetings and respins. 3. Effective. Specifications provide the marching order for all to follow.